will be part 2 of basic principles of work in the laboratory, and we will go through the classical methods of analysis. Basically, it will be volumetric and gravimetric analysis. These are two types of analysis that you use very often in a food analysis lab. And we do a large number of analytical procedures using volumetry and gravimetry. So, what is volumetric analysis? Volumetric analysis is an analytical method which involves using two solutions and measuring those two solutions. One solution is called the titrant, or it is the standard solution, for which you know the concentration because you have made the standard solution very accurately with an accurate concentration. And the second solution that we use is the solution of the analyte, which is an unknown concentration. So in volumetric analysis, we can determine the unknown concentration by carefully controlling the volume of the titrant and the unknown. If you look at the equation in volumetric analysis, you have the analyte A with A moles and the titrant T, which gives you product. One of the basic requirements of volumetric analysis is there should be a stoichiometry between the analyte and the titrant. So an example of a very common volumetric analysis is what you would have probably done in your +2 or in your undergraduate, that is the titration of either hydrochloric acid or sulfuric acid against sodium hydroxide. So the stoichiometry here you can see is that 1 mole of sulfuric acid will react with 2 moles of sodium hydroxide to give you 2 moles of water and 1 mole of sodium sulfate. So this is a balanced equation, or it shows the stoichiometry between the analyte and the titrant. So what is titration? All of you know what is titration and you have all done this in the laboratory. But just to recap and refresh your memory, we take the aliquot, generally of the unknown solution, in an Erlenmeyer flask or a conical flask. We measure the volume using a pipette, a volumetric pipette, and then we add the standard solution or the titrant from the burette. This technique is known as titration, and the reaction will come to completion at a point which is called as the end point or the end of titration, which will be shown by the change in the color of the indicator. Either the color of the indicator will disappear or the color of the indicator will appear. The end point is very close to the equivalence point. Please remember, these are two different terms, end point and equivalence point. Equivalence point is the point at which the analyte is totally consumed. That means it is the theoretical end of the titration. So here in the previous equation, the end equivalence point comes when 1 mole of sulfuric acid has been consumed by 2 moles of sodium hydroxide. That is the stoichiometry of it. So coming to differentiate between what is endpoint and what is equivalence point or equivalent point, the point at which the reaction is observed by the human eye to be completed is the end point. The endpoint is only a signal that tells the analyte to stop adding the reagent from the burette and to take the final reading. Generally, the endpoint is observed with the help of an indicator, a color indicator, or it is uh, observed using a pH meter or a potentiometer. So where the pH is 7.0, that will be the endpoint. Equivalence point, as I said, is an equivalence where a stoichiometric amount of the titrant is consumed by the analyte based on the stoichiometric equation. And in some of the equations and some of the examples that I will show you in the problems, you can see that it is 1:1 or 1:2 or 1:3. For example, when you do a citric acid titration, the stoichiometry is that 1 mole of citric acid will react with 3 moles of sodium hydroxide. That is because it has got 3 protons that it can donate. Now, finding the end point, as I indicated, the end point is observed by a change in the physical property of the solution. So most often, you will see the end point for a color by a color change, and this can arise without adding an indicator or by adding an indicator. As you will see in this titration, where we use the titration of, it's an oxidation reduction titration, where we will titrate potassium permanganate against oxalic acid. So the first trace of the purple color that you see on the right hand side is the end point. So here, as soon as you add the permanganate to the oxalic acid, which is heated, you will see that a pink color forms and then disappears when you shake the Erlenmeyer flask or the conical flask. And at the end point, when the oxalic acid is all consumed by the potassium permanganate, in this stoichiometry, you will see the appearance, that is the pink color will appear and it will not disappear. So it stays permanent and the excess of permanganate shows the end point. You would have done most of your titrations with phenolphthalein or with methyl orange or methyl red. In methyl orange, when we do the titration, as you will see, it is the disappearance of the orange color and the appearance of a straw yellow color. Whereas in phenolphthalein, generally it is the appearance of a color similar to potassium permanganate. So look at the stoichiometry of this equation over here. So you see here, for every 2 permanganate ions, there will be 5 moles of oxalic acid, and it will give you 10 moles of carbon dioxide and magnesium 2, manganese 2 plus. When you're doing volumetry, it is very important to learn and remember the concentration, the way you express the concentration of the titrant as well as the unknown solution. So we have gone through this in part 1 of this webinar. It is an expression of the quantity per unit volume or unit mass of the substance. So here it is how much of solute is there per unit volume of the solvent. The solute generally is the minor species, whereas the solvent is the major species. Most often, we normally express the concentration in molarity with capital M, or it is moles per liter. Not so often, we also express as molality, and you know the difference between molarity and molality. Here, it is the moles of solute per kilogram of the solvent. So expression of concentration is very important. So other expressions of concentration that we use and you are now all aware of is the percent composition, which can be either mass by mass, or in older books it is always given as weight percent. So that is mass of solute by mass of solvent into 100, or it could be mass by volume, that is mass of solute by volume of solvent, or it could be volume by volume. So in whichever way the concentration is given or known, you should be able to interconvert, or you should all learn how to interconvert between percent, molarity, molality, weight percent, equivalence to molarity, etc. These are very important in the volumetric analysis. Another common expression, especially in terms of the additives and the contaminants, is parts per million or parts per billion. So you know that 1 part per million in terms of volumetric will be 1 microgram per milliliter or 1 microgram per gram if it is water. So when understanding these concentrations, why don't you try these calculations? Convert 37% weight percent of hydrochloric acid into molarity as well as molality. And here the density of the hydrochloric acid is given, which is required. And when we express in ppm and ppb, you can see, for example, this soft drink here contains approximately 38 ppm of aspartame. So what does this mean? It means there are 380 micrograms of aspartame per liter of the drink. So if you consume 250 ml of this cola, you will be getting 70 micrograms. Your intake of aspartame will be 76 micrograms. So imagine if you drink about 2 liters, calculate the amount of aspartame or this foreign chemical that your body is exposed to. The equipment for titration, all of you know, but we should review this, is you will use a volumetric pipette. It has to be a to deliver pipette, and it should be of class A, required for measuring accurate and precise volumes. Your burette also has to be class A, and it is a to deliver burette. Your volumetric flask should be a class A, and it should be a to contain flask, that is TC. It is used to make accurate solutions of the standard or the titrated. You have conical flasks, also known as Erlenmeyer flasks, which are used for mixing the titrant and the unknown solution. Wash bottles are required and funnels are required for transferring the liquid or the standard into the burette without spilling it. Standard solutions. What is a standard solution? It is a solution whose concentration is accurately known. A standard solution is prepared not by just dissolving a measured mass of substance into a known volume of solution. There are certain properties and certain requirements for a standard, because the chemicals that we use in making solutions come of different purity and different grades. So in a standard solution, we have to use a standard which has very high purity and also which does not decompose. So in volumetric analysis, we use what are known as primary standards. They are known as primary standards because these chemicals are so pure that the amount in moles can be calculated very accurately from their mass and therefore are called as primary standard. So to be a primary standard, what are the qualifications? One is it should be of high purity so that the mass of the material that you weigh is, you can get the exact concentration. Generally, it must be 100% pure. It should be highly stable in the dry form. It cannot decompose. It cannot degrade. It cannot lose its water of crystallization. Neither can it absorb any moisture. So it has to be in a very stable form. It should be in the anhydrous form, because the hydrated water or the water of crystallization or hydration does not allow the exact composition to be known. Generally, it should have a high formula mass so that the errors, when you have a higher mass, the error is much lower. Inexpensive, and examples of primary standards that you use in an analytical laboratory are anhydrous sodium carbonate, sodium borate, and in terms of acid, we use oxalic acid and potassium hydrogen thalate. So even if you don't have a pH meter, you can use potassium hydrogen thalate. So here are the properties of some of the primary standards that are commonly used in volumetric analysis. Potassium hydrogen thalate, which generally you can detect by using phenolphthalein. The endpoint is observed with phenolphthalein. You have potassium hydrogen iodate. The endpoint is between pH 5 and 9. Then you have tris, which is tris hydroxyamino sodium carbonate, and sodium borate. Others are there in the list, but this is what is used commonly. So I thought you should know about these common primary standards. So there is an art in making a standard solution, and this is you weigh very accurately in a calibrated balance, weigh by difference the primary standard, transfer it into a volumetric flask using a funnel, and then fill it with water halfway and dissolve the primary standard completely, and then wash down the funnel and the sides of the volumetric flask to the calibration mark shown on this. Invert several times, and then you have a good or an accurate primary standard solution. So what are the good practices that you must follow in titration procedures? In many laboratories, I have seen that when they are transferring the liquid from the volumetric standard flask, that is the titrant, into the burette, this is thing, they generally try to pour it directly into the burette. But a good practice is to use a funnel so that no solution remains on the outside, it is spilled on the outside. A second good practice is when you're reading taking the reading of the burette, put a black paper behind and read the lower meniscus. You all know from the classes on water and the basic principles that you must read the lower meniscus. Another one is to see that in your burette there is no leak and the stopcock rotates easily and it is airtight. And of course, using personal protection. One may think that volumetric analysis is a very safe analytical method and personal protection is not required, but you will have to wear the gloves. And the other one is when you are finished, when you are titrating with the burette. In case there are small remnants of the titrant over there, we generally keep washing down the tip of the burette. So these are some of the good practices in while doing titration. Now, coming to the titration itself, what are the types of titration? Commonly, all of you know the acid-base titration. That is, an acid and a base are titrated against each other. We have the redox titrations, where you have the reducing, one of the components is reduced and the other is automatically oxidized. The best example is the titration of oxalate with potassium permanganate. Here, the permanganate ion is reduced to manganese ion and the carboxylate ion is oxidized to carbon dioxide. So this is a redox titration. That means using two, a reducing agent and an oxidizing agent. The third is the precipitation titration, where you do the titration to see the appearance of the precipitate. For example, for determining the chloride, we can titrate with a known concentration of silver nitrate. The last one is a complexometric titration or the complex formation, where a compound which chelates a metal is used for the titration. So here generally, if you see, EDTA is used because EDTA can complex several metals stoichiometrically. That means 1 mole of metal is complexed by 1 mole of EDTA, and this is a hexadentate. You know, it has got the EDTA is hexadentate, so the metal can chelate with 6 different parts or form the bonds with 6 different molecules or atoms of ethyl diamino tetraacetic acid, that is EDTA. So let us look at the acid-base titration. If you look at the basic definition by Arrhenius, acids are species that can donate a proton, and bases are species which can donate a hydroxyl group, that is a OH. Bronsted, on the other hand, defined an acid as one which can donate a proton and a base as one which can accept a proton. So neutralization is the reaction between an acid and a base, where the proton is, the donated proton is accepted by the base and it forms a molecule of water and neutralization occurs. The neutralization reaction can be used to determine unknown concentrations. So when we talk of acid-base titrations, you know that we have strong acids and strong bases, and we have weak acids and we have weak bases. So the 4 different types in the acid-base titration are a strong acid with a strong base, example HCl, or sulfuric acid with sodium hydroxide, a weak acid against a strong base, that is acetic acid versus sodium hydroxide, a strong acid versus a weak base, HCl versus ammonium hydroxide, and a weak acid and a weak base, which is acetic acid versus ammonium hydroxide titrated. So these 4 titrations, you can have titrations with any permutation and combination. So in the acid-base titration, the indicators are used, which are the acid-base indicators. These indicators are either acids or bases, or you can use a pH meter to come to the end point. So here in this figure that you see, here methyl orange is used as the indicator. So in the beginning, it is red in color or orange in color. Halfway through the titration, and when it is neutralized, you will see this is the end point. Commonly in food analysis, This type of titration is done to determine the acid content in juices, milk and wine, the acid content in vinegar, ketchup, and the P and M value in water acidity and alkalinity, free fatty acid content of oils and fats, alcohol acidity of wheat flour and maida, and several more. So the indicators that we use, are those which undergo a change in color when the end point of the titration is reached. There are two types of indicators. One is the acid type of indicator and the other is a base type. These indicators are themselves weak acids or its conjugate base. So here you have methyl orange as an indicator. You see it changes to red at 3.1, that is in the acidic pH, and we have seen it over here. So this is at acidic pH. And then it turns towards more the yellow color, or what you see on neutralization at 7. What you see is this color, or what we say as the straw yellow color. Common acid-base indicators and their pH range is given in this table. And commonly what we use in the laboratory, you have seen, you would have used bromothymol blue, you would have used methyl orange, you would have used methyl red, and you would have used phenolphthalein and maybe thymol blue. So you look at the base indicators, that is which showing number 2. So you see in the acid, these show a color. But however, when they reach the end point, the color changes. Whereas you look at phenolphthalein, that in the alkaline pH range or at pH 7, you will see that it gives the color. So in acid, it is colorless, and just as the pH reaches 7, it will become pink. So several types of color indicators, which are either weak acids or their conjugate base forms, are used in acid-base titration. So what are the requirements for an acid-base titration? That means an acid being titrated by a base. One, you should be able to write a well-defined reaction between the titrant and the analyte, and there should be a stoichiometry. The reaction between the acid and the base must be rapid. There should be no side reactions and no interferences. They must have some indication of the endpoint with a color indicator or conductivity or a sudden increase in pH, and a known relationship between the endpoint and the equivalent. So you look at this titration of hydrochloric acid with sodium hydroxide. So here the titrant is sodium hydroxide. So as you add sodium hydroxide, you see there's a very slow change in color as it goes on to reaging. But when it comes to the inflection point, there, just by adding a small amount, you see there is such a drastic change in the color of the indicator because of the drastic change in pH. So pH 7 is the equivalence point, whereas the end point with our color indicator will also be close to this. Then coming to the redox oxidizing reduction titrations. Here, as I said, one is an oxidizing agent and the other is a reducing agent. So here, permanganate, potassium permanganate, is titrated with oxalic acid. And we do this as a hot oxalic acid titration, where the permanganate ion is reduced to manganese ion and the oxalate ion is converted into carbon dioxide. So here in this oxidization reduction reaction, there is a transfer of electrons from one substance to the other. So from the manganate ion, it is transferred to the oxalate ion. And here an indicator is not required because there is a self indicator, and as soon as you have excess of potassium permanganate, you will get a pink color, and that shows the end point and the equivalence point. This type of oxidation reduction reaction you have all done, and we have discussed this, is determining the reducing sugars in juices, where you use filling solution and you have the cuprous oxide, which is the cupric oxide, which is converted into cuprous oxide. So examples are determination of vitamin C in juices and sulfur dioxide content in wine and the peroxide number in edible oils. So remember, you have to have an oxidizing agent and a reducing agent in the titration. In the complexometric titrations, these are based on forming the complex. So here, as you see, EDTA is the common titrant for these complexometric titrations, because it can complex stoichiometrically a large number of metals such as magnesium, calcium, iron, and it can be used to determine the content of these metals. It is a hexadentate ligand. That means it ligands with 6 different atoms. So you have 1, 2, 3, 4, 5, 6, and it gives a 1:1 stoichiometry between the metal and EDTA. And the equivalence point here is determined by using an indicator, and generally the indicator used in these titrations is the areochrome black. Then when doing these titrations, whether it is an acid-base titration or a complexometric titration, there are 3 types of titrations that are possible. One that all of you know is a direct titration, where the analyte you add, the stoichiometry between the analyte and the titrant, the value gives you whatever value you get the titrant, you can calculate the analyte concentration. That is a direct volumetric analysis. Okay, so the titrant consumed is directly equivalent to the analyte concentration. Example is acid content in wine and vinegar, where they are directly titrated with either sodium hydroxide or potassium hydroxide. Then you have a blank compensated titration. So what is this blank compensated titration? This is a titration where the solvent in which the analyte is dissolved also will react with the titrant. So it could be a weak acid or a weak base, and it could react with the titrant that is in the burette. So therefore you do what is known as a blank titration without adding the analyte. Then you do a titration, a second titration by adding the analyte, and the analyte concentration will be obtained by subtracting the blank value from the titrant value. So this is a blank compensated titration, and this type of titration is used to determine the acid number of free fatty acids in edible oil, because oil is hydrophobic, it is not soluble in water, and titrations are between aqueous solvents, remember. So we need to have the oil dissolved in it, and we generally will add a hydrophobic solvent, and then to bring about the miscibility, we will add some base or acid so that it goes into solution. The last one that you see over here is a back titration. So what happens in a back titration is these reactions are very slow reactions, or they produce side reactions, and it is very difficult for us to actually find out the analyte value. So here what is done is an exact volume of excess titrant or reagent is added to the analyte solution. So the analyte and the titrant will react with in stoichiometric amounts. Now there will be an excess of the titrant A. So you titrate that against a second um, solution, which is B, and the difference titrant A value minus titrant B value will give you the analyte, the stoichiometry, or the value for which is used by the actual analyte. So here, after you have to add excess titrant to the analyte and wait for the reaction to go to completion. After this reaction time, the excess reagent is back titrated with a second titrant. So if the first titrant is called A and the second titrant is called B, then the volume of A minus the volume of B gives you the equivalent of the unknown analyte. So this is known as a back titration, and most of you would have used it, especially in nitrogen estimation by Kelda. So here in this method, you see that you liberate the ammonia from the sulfates by using steam. The ammonia is captured in excess boric acid so that you have the ammonium borate formed, and then this is titrated with HCl. So the excess borate that is formed, the excess borate will be actually subtracted and you get the titrant value. So this is where you use back titration. Okay, so where you allow the reactant. So in Kjeldahl distillation, you allow the ammonia to be captured in excess of boric acid, and then the excess the ammonia will react with the boric acid to form ammonium borate, and then you titrate with hydrochloric acid. So in volumetric analysis, calculations are very important and they revolve around values, terms such as moles, the molarity, and the equation C1V1 is equal to C2V2, and where C is either the molarity or the normality of the titrant and the unknown. So generally in a volumetric analysis, you would first write a balanced equation or know the stoichiometry, calculate the normality or molarity of the standard reactant, if not known, then calculate the number of moles of the reactant, see how many moles of the reactant is used in the reaction, and then calculate the mass of the analyte. So in volumetric analysis, what are the errors that we can generally make? The standard errors that we can make are errors with your titration by adding excess. Those are the random errors. You can correct those random errors. But however, there are some system errors which cannot be corrected, and those contribute to the uncertainty. Now, this is, in class A, you have been given tolerance limits for burettes and pipettes. So the uncertainties associated with the volumetric glassware are for the pipette, for the burette, and for the volumetric flask. So these are system errors which you cannot do anything, or neither can I. But the errors which are associated with making the standard, accurately weighing the primary standard, making up the standard solution, all also contribute to the uncertainty if your balance is not calibrated. All these add to the uncertainty. So now let us see a few examples of the titration and how to do calculations. So in this example, 30 milliliters of 3 molar hydrochloric acid is titrated with sodium hydroxide to form sodium and chloride. The question is, how many millimoles of sodium hydroxide are consumed in this reaction? So step one is to write the stoichiometric equation, which is very simple. HCl plus NOH gives you NaCl plus H2O. So it is 1 mole of hydrochloric acid with 1 mole of sodium hydroxide. So the molar ratio is 1:1. So the number of moles in the final hydrochloric acid should be equal to the moles of sodium hydroxide. Now you know the volume of hydrochloric acid and you know the concentration of hydrochloric acid. So therefore you can calculate the moles of hydrochloric acid. So here the moles of hydrochloric acid will be equal to molarity multiplied by the volume. So you have molarity is 3 and the volume should be in liters because molarity is moles per liter. So multiply by 0.03, and so what it gives is 0.09 moles, which is equivalent to 90 millimoles of sodium hydroxide. So 90 millimoles of sodium hydroxide are consumed. Read the question very carefully because the question says millimoles. It doesn't say moles. So therefore, give the answer 90 millimoles of sodium hydroxide are consumed in the reaction. Let's go to another example. Here you have 50 milliliters of 0.5 molar calcium hydroxide are required to fully titrate 100 milliliter solution of sulfuric acid. So what is the concentration of the sulfuric acid? So here first step is to use the equation C1V1 is equal to C2V2. Then you put down, the molarity of the volume of the acid. You do not know the volume of the, you don't know the concentration of the acid. You know the molarity of calcium hydroxide and you know the volume of calcium hydroxide. Now here I did not change it to liters because on both sides of the equation we can use milliliters. If on one side of the equation you have a liter, you cannot use milliliter on the other side. On both sides of the equation, the units for the unknowns should be the same. So molarity, so you have this as molar and thing. So now your answer is using this, and by algebra, if you do it, what you get is 0.25 molar is the concentration of sulfuric acid. So remember, in this equation, if you had to do a problem like the previous one, here the equation would be for 1 mole of sulfuric, every mole of sulfuric acid reacts with 1 mole of calcium hydroxide to give you 2 moles of water. Okay. The third example, an example which you would do in the laboratory, in a food analysis laboratory. So here, a 50 ml sample of orange juice requires 17.62 milliliters of a 0.04166 molar sodium hydroxide to reach the phenolphthalein endpoint. Now, express the sample's acidity as grams of citric acid per 100 ml. So given to you is that the molar mass of citric acid is 192.13. Remember, Citric acid is a triprotic weak acid. That means it can donate three protons, and the phenolphthalein end point will correspond to the final equivalence point. That is when all the three protons have been completely neutralized. So it will go to the third equivalence point. So what is the first step? The first step is to write the equation here. So the titration equation, because it says it's a triprotic weak acid, that means it can donate three protons. So the three protons can be accepted by 3 moles of the sodium hydroxide. So 3 protons are accepted by the base, and what you get is 3 moles of water. Okay, so here the H8 is reduced by H5. So this is the stoichiometry. So therefore, each mole of citric acid consumes 3 moles of sodium hydroxide, right? So the moles of sodium hydroxide is equal to, you know the volume and you know the molarity. We know that molarity is equal to moles by volume, or moles is equal to molarity into volume. So you have 0.04166 into 17.62. Here we are expressing in molarity. So therefore the volume must be converted into liters. So what you get is there is 0.0073 moles of sodium hydroxide. We know that for each mole of citric acid, 3 moles of sodium hydroxide are consumed. So how much of citric acid is consumed by 0.0073? You divide this by 3. So what you get is 0.00244. So the moles of citric acid consumed is actually 0.00244. And here the mass of citric acid is equal to moles into molecular mass. So molecular mass is given to you, and so therefore the 50 ml sample of orange juice contains 0.0470 grams. Now, if you have been asked to express it in 100 ml, so that's where this 50 ml comes, you have to know. So this is in 50 ml, so therefore in 100 ml, the mass of citric acid in 100 ml will be equivalent to 0.094. So always write down the equation. Remember the equations, that molarity is equal to moles by volume, and you can do any one of these problems. So the last example, let us see, which is an example of a back titration. So here we are trying to determine the protein content in a soya protein enriched pasta, which is done by Kjeldahl analysis. So after digesting 1.181 gram of pasta, the nitrogen is oxidized to ammonium, converted to ammonia with sodium hydroxide, and distilled in a collection flask containing 50 milliliters of 0.01035 moles of hydrochloric acid. The excess hydrochloric acid is back titrated with sodium hydroxide, requiring 21.3 milliliters to reach the end point of bromothymol group. You have been asked to calculate the percent of protein, assuming that 1 gram of nitrogen is equal to 6.2 grams of protein. That is the conversion factor. So here, this is an example of a back titration. So the two reactions are, in flask 1, what you see is the ammonia is reacting with the hydrochloric acid, that is the excess hydrochloric acid that you have added. So you have added 50 ml of hydrochloric acid. In flask 2, the reaction is between the the hydrochloric acid and sodium hydroxide. So there we know the stoichiometry is 1:1, and that is occurring in flask 2. So calculate the volume of hydrochloric acid consumed in flask 2. So volume of hydrochloric acid consumed in flask 2 is equal to the concentration multiplied by the volume, and the concentration of sodium hydroxide, which is given. This is the concentration of sodium hydroxide multiplied by the volume of sodium hydroxide is equal to the concentration of HCl multiplied by the volume. If you rearrange, you do this, because you see this is your HCl concentration. So what you get is 23.42. So this shows that 23.42 milliliters of HCl is remaining in the it has been consumed in flask 2. So originally you added 50 ml. So the actual volume of hydrochloric acid consumed by the ammonia will be 50 minus 23.2, which is equal to 26.58 milliliters of hydrochloric acid. So how many moles is that? You have the concentration of hydrochloric acid into that. So you get the moles of hydrochloric acid is 0.00276 moles of hydrochloric acid. We know 1 mole of ammonia contains 1 mole of nitrogen of 14 grams. So therefore, the amount of nitrogen which is present is 0.386. And this you multiply by 6.25. This you multiply by 6.25. So what you get is, in that solution, you have 0.241 grams of protein content. This 0.241 gram is present in 1.18 grams of the pasta. So 100 grams of the pasta will contain 20.44 grams of protein. So here is a very good example of a back titration where you have added excess hydrochloric acid, you have taken in the ammonia, and then the unused hydrochloric acid is titrated against a known concentration of sodium hydroxide. Now let us shift gear and we will move to gravimetric analysis. So gravimetric analysis is analysis which uses mass. So you measure mass over here. So the gravimetry, gravi means weighing and metric means measure. Here a precipitation or a volatilization method is based on the determination of mass of the substance. So it includes all analytical methods in which the analytical signal is a measurement of the mass. So types of gravimetry, you have done this but may not have used these words. You have volatilization gravimetry, where you remove one of the constituents by heating so that it evaporates, or you chemically decompose it. The best example is the moisture content of all the foods that you carry out in a food analysis lab. So here you're volatilizing the water, removing the water, and weighing the anhydrous. You have precipitation gravimetry, where you can precipitate the analyte by a known precipitant and weigh the precipitate, because the precipitate formed again is in stoichiometry, and this is used, for example, for determining the chloride content in salt, the chloride content in water, drinking water, etc. Then you have electrogravimetry, where it is a method used to separate and quantify ions. Usually it is done for metals, where you use an electrical system and you deposit the metal ions either on the anode or the cathode and weigh the increase in the weight. And then you have particulate gravimetry, where you can actually get the mass of the particles by using filtration or by extraction. So all of this is gravimetry, where everywhere you have a measurement of mass. So in gravimetry, you have to remember that there is a conservation of mass. That is, matter is neither created nor destroyed. So A plus B is equal to A plus B. So you cannot destroy the matter. So here, that is why in gravimetry, it is a mass change or a change in mass that is proportional to the amount of analyte in the sample. So it all involves a conservation of mass. So when you're determining the moisture content in bread, you know the mass of water in the bread is the difference between the sample's final mass, that is where you have completely removed the water, and the initial mass. So in precipitation gravimetry, an insoluble compound forms when a precipitating reagent is added. Very good examples of this are, if you add silver nitrate to a solution which contains chloride, you will get silver chloride, depending on the amount of chloride that is there. You collect the precipitate and weigh the precipitate, and that will be in stoichiometry to the amount of silver nitrate that has been added. Theory and practice of precipitation gravimetry. There are two attributes in precipitation gravimetry, that is about the precipitate. The precipitate must be of low solubility, of high purity, and of a known composition. Okay, and the precipitate must be easy to separate. Now, it should not be that you visibly see a precipitate and you cannot separate it by either centrifugation or by simple filtration or by filtration using vacuum. So steps in precipitation gravimetry: you dry and weigh the sample, you dissolve the sample in a solvent, add precipitating reagent in excess, you coagulate the precipitate usually by heating, separate the precipitate from the mother liquor, wash the precipitate and dry and weigh it to a constant weight. And from the weight of the precipitate, you can calculate the analyte. For example, silver. So if you want to measure or chloride, so if you are doing a chloride estimation, you add silver nitrate in excess, silver chloride will be formed. That is, 1 mole of silver will react with 1 mole of chloride to form silver chloride. This precipitate is dried, and from the precipitate's dry weight, you know the molecular weight of silver chloride, you know the molecular weight of chlorine, and you can calculate the amount of chlorine in the unknown. So in the precipitate, what is important is, in precipitation gravimetry, is that the particle size is very important and the precipitate has to be filterable. That means the particles have to be large enough to be caught. So ideally, they should produce crystals, and we should not have colloidal suspension, because in colloidal suspensions, you cannot get very good filtration. Even if you have a colloidal suspension, in colloidal suspension, you see that the size of the particles ranges from 10 to the power of -6 to 10 to the power of -4. And they will have no tendency to settle. So it is very difficult or impossible to filter a colloidal solution. Whereas in a crystalline solution, the sizes are big. They range from 10 to the power of -1 to 10 millimeters. They will settle spontaneously. They will be readily filterable. and their purity will be much better than the colloidal suspension. So those of you who have had chemistry and done your +2 or in school or in lab, when you add silver nitrate to sodium chloride solution, you will see a precipitate which settles immediately. So that is the type of precipitate we are looking for in gravimetry. So how does a precipitate form? The theory is there is nucleation. First, a small stable particle is formed, and then the bigger particles, the larger particles, they surround the small nucleus and they grow, and you get a good precipitate. So how do you actually characterize this precipitate and understand what are the requirements? This goes by the formula for relative super saturation. It is defined as the relative supersaturation is equal to the solute's actual concentration minus the solute's concentration at equilibrium divided by the solute's concentration at equilibrium. So in the numerator, you have Q minus S, which is a measure of the solute's supersaturation. So if you want to have a big RSS value, and that is what you want for a good precipitate, then your Q minus S has to be very high. So a large positive RSS value has a high rate of nucleation and a good precipitate is formed. If your RSS is small, it is more of a colloidal solution because your solute's concentration at equilibrium is very high. So when S is very big, RSS becomes very small. And so the precipitation is more likely to occur by particle growth than by nucleation. So this is how RSS, that is the relative supersaturation, is related to nucleation and particle growth. So here are two examples of the same precipitate. This is lead chromate precipitated in two different ways. So the goal in precipitation gravimetry is to get a crystalline precipitate, and this, how can you get a crystalline precipitate, is you can achieve this by increasing S. So you can change the temperature or the pH. And if you want to decrease Q, you can use dilute solutions, add the precipitating reagent slowly, and stir the solution. So what you see in beaker A is when you combine lead nitrate and potassium chromate, it forms a precipitate under conditions of high RSS. So it forms the precipitates very rapidly and they are very small particles. Whereas in B, you have added, you take a warm solution of lead nitrate and along with chromium nitrate and potassium bromate. So you get a precipitate of lead chromate. And here you have oxidized the chromium 3 plus to chromium 2 minus, and the potassium lead chromate which is formed has a low RSS, and the precipitate you get over here is of much larger particles and it is crystalline. So you can get crystalline precipitates by either using dilute solutions or by elevating the temperature or the pH control. So that is why in all these precipitation gravimetric methods, you will see that these instructions are given on keep the pH at this, or keep the temperature at this, or use a dilute solution of the precipitating reagent. So techniques to promote and get the crystalline precipitates, as I said, one is raising the temperature, two is adding the precipitant slowly with vigorous mixing, and three is to keep the volume of the solution large. That means dilute the concentration of the analyte so that they are very, very low. The solutions are very low and the precipitate will form. So how do you collect the precipitate? Several methods are available. You can use a filter flask with a Buchner funnel. So a filter flask has got a side arm. Okay. Then you have the filter paper, which is very important. And or you can use a glass frit. You use a filter adapter to put it into the vacuum flask, heavy walled vacuum rubber tubing, and this must be connected to a vacuum source, either water or to a vacuum pump. So this is the setup which is used for suction filtration. So now let us see about the filter paper, which is very important. So to collect the precipitate, whichever precipitate you have got, whether it is a crystalline precipitate or a fine precipitate, we need to use filter paper. So which filter paper do you use? Why does the procedure say use Wattman number 40 or Wattman number 41 or X or Y? You have to understand that these filter papers, whichever company it is manufactured by, are given numbers based on the speed, based on the pore size, and whether the filter paper will have any ash content on ignition. So you will see that you are asked many a time to use the ashless filter paper. So why do we need to know all these things? So speed is how quick the supernatant will pass through the filter paper, and this depends on the pore size. So the bigger the pore size, the faster the filtration will be. But when you choose the pore size of the filter paper, you should see that the precipitate or the small particles of the precipitate do not flow through the filter paper. So filter papers are rated as fast, medium and slow. So the fast retains particles greater than 20 to 25 millimeters. Medium fast retains particles greater than 16. Medium 8 and slow 2 to 3. Now you can use a medium filter paper if you do not have a fast, or you can use a medium if you do not have a medium fast, but it will take longer. But if you are asked to use a slow filter paper, you cannot use a fast filter paper or a medium fast filter paper or a medium paper, because all your particles which are of this size will flow through. So proper choice of the filtering speed and the filter paper is important. Filtering too fast, you may fail to retain some of the precipitate. And if you filter too slowly, it will take too long and it may clog the pores. So ashless filter paper is, whenever we are transferring the precipitate, very often it is aqueous, so the filter paper becomes soggy. It is not possible to scrape the precipitate, and we generally transfer the whole filter paper because the paper is very, very hygroscopic, and if you want to get the exact precipitate mass, you have to transfer it stoichiometry. And once you transfer it, the water is evaporated, and then the paper is ignited to give you carbon dioxide and water, and there is no ash. And this is known as ignition. So the ash content of filter paper is described as ashless or low ash grade, which means that when you ignite the filter paper, which is made up of cotton, no ash will remain. So in the filter papers, you have quantitative filter papers and you have qualitative filter papers. So in gravimetry, we will use only quantitative filter papers because the precipitate has to be recovered 100%. So quantitative filter papers are made out of 100% cotton linters with an alpha cellulose content of greater than 98, and they are available in ashless, hardened low ash, and hardened ashless versions. Qualitative filter paper are general purpose filter papers which are used in a vast range of applications, mostly in qualitative techniques to remove particles when you're making solutions. And these are also manufactured with 100% linter cellulose. They are available either in circle or in sheet or in reed. The standard filter papers are for general use. They are made up of 100% cellulose, and these are the filter papers you will find that we use in school and in laboratories, college laboratories, etc. Most important is in gravimetry, we must use quantitative filter papers, which are ashless or hardened low ash or hardened ashless versions. So in this table, I have given a comparison of the different ashless filter papers which we use for gravimetric analysis. So here you see we are all familiar with Wattman, but we need to understand the difference in these numbers 40, 41, 42, 43. So you see here it is all the pore size that matters. Okay, so 41 is a fast, this is medium fast, this is medium, and this is a slow filter paper. So you see the slow filter paper as we saw earlier, 2.5. So particles of 2.5 are retained, and so you see that filter paper is used for fine particle retention. Now you have the same filter paper with fine particle retention, but you have got a different number 50. So what is the difference between between number 42 and 50 is this 50 is hardened glaze silver, which is suited for vacuum filtration. So you are sure that it doesn't tear when you apply very high vacuum, and it can withstand wetting. So whenever you buy filter paper, you should understand what is these numbers and what it is suitable for. Several companies supply all with different numbers, so you have to see which is compatible with which. For gravity filtration, all of you know this is how we fold the filter paper into it to get a cone, and we generally tear off one corner of this so that there is some air going into it and it filters. Precautions to be taken are that you transfer this without spilling all of the precipitate and you put it along the sides. We generally have filter stands which can be used. Filtration can also be carried out not only with filter paper, but you can use filtering crucibles. Two types of crucibles are available. One is the fritted glass crucible and the other is a Gooch crucible. So if you look at the fritted glass crucibles shown over here, the base of the crucible has got a fritted glass. This fritted glass has a different pore size to maintain different types of precipitate. So the coarse fritted glass retains particles greater than 40 to 60, so it is very fast. The medium one retains 10 to 15, and the fine retains 4 to 5.5. See, these fritted glass crucibles they can be this type, or this can be attached to the suction flask, and the liquid removed, the filtrant removed, or the supernatant removed by using a vacuum trap. The Gooch crucible, the name Gooch came from its discoverer. is a porcelain crucible which has got a perforated bottom. Can you see this perforated bottom? And we use a glass fiber mat in this to retain it. The glass fiber is much stronger than the filter paper, and the precipitate can be quantitatively transferred, similar to what we saw about the filter paper. So instead of using gravity, here it is pulled through by a vacuum aspirator or pump. Whenever you're doing vacuum filtration, please be very careful that this solution does not come above the side arm. If it comes above, then water gets sucked into your pump, and your vacuum pump, will be destroyed. So in these fritted glass crucibles, they come with different porosity, and they come with the numbers P500, P250, P100 also. So you also need to know, just like how you know Wattman number 40, Wattman number 41 also, in the fritted glass filters, you need to know what these numbers, that is the P numbers, specify. They specify the pore size. So you see those which hold bigger particles are the extra coarse, those which hold the medium size are called the medium, and those which hold the fine. Now, precautions that you need to take over here is these fritted glass crucibles, especially the fine ones, tend to get easily blocked by the precipitate, and you will not have flow. Drying the precipitate is another very important factor, and generally the precipitates are dried by using a convection laboratory oven, and temperatures of 110 degrees centigrade are sufficient. But you have to be sure that your drying procedure does not degrade the precipitate and it remains in its form. If you want to use higher temperatures, then instead of the laboratory oven, we use the muffle furnace, where not only is the precipitate decomposed, but even the filter paper will be completely decomposed. Okay, so the filter paper absorbs moisture. We must remove it before weighing the precipitate. So this you can accomplish by taking the folded filter paper with the precipitate into a porcelain platinum crucible, gently heating it, and then charring the filter paper. Then you have, that is precipitation gravimetry. Now let's come to the volatilization gravimetry, which you are all very familiar with. So here the experimental design is very simple, that you actually remove the vapors by heat, and the resultant analyte is weighed. So in a very simple experimental design, you use a crucible or a pan for volatilizing or decomposing the precipitate using either a Bunsen burner or a laboratory oven or a muffle furnace. And where do we use volatilization gravimetry? In addition to the vaporization of the moisture, you are using it to determine the inorganic ash content of a food, the total acyl content of a food, determination of the dissolved solids in natural waters, determining the moisture content of a variety of products, and determining the elemental analysis of organic things. So for moisture content, we do the volatilization at 110 degrees or 133 degrees as the procedure specifies. But when you want to do the inorganic ash content or the total ash content, you actually first take the precipitate, char it, allow the paper to be ashed, and allow the complete decomposition of the analyte, so that carbon is removed as carbon dioxide, nitrogen is removed, and oxygen is removed. So only what is remaining is the ash. The ash is the heavy metals, the silica, etc. Particulate gravimetry is used when the analyte is present in the particulate form, and it can be easily separated from its liquid, gas, or solid matrix. So here the separation is possible and the mass can be determined without relying on the chemical reaction. So two methods of separating particulate is filtration and extraction. Filtration is like if you are doing the suspended solids in water. So what you do is you take the water and you filter it and weigh the filter paper, remove the water, and that gives you the weight of the suspended solid. So filters for liquid samples are constructed from a variety of materials. So cellulose fiber, glass fibers, cellulose nitrate, and a PTFE. So depending on what you want to do, you can use the different filters to collect the particulate matter. So for particulate gravimetry, we can also use the sieving procedure. So sieves are available and you can sieve. These sieves have got different mesh sizes. So you can stack the sieves of different mesh size. You can isolate particles with several narrow ranges and then weight of each of the particles in the different sieves can be used. So this is particulate thing. So particulate gravimetry is used to identify extraneous matter, in terms of most of the cereals and legumes, you sieve it through a different sieve. It is used to actually analyze the mud and sand in different grains. So the sieves, when you put the sieves, and the sieves are arranged such as the highest diameter is on top, followed by the other diameter. So the way in which the sieves are arranged is from the higher diameter to the lower diameter. So in the sieve, which is on the topmost, you see particles which are greater than 1700 millimeters will retain. In the last sieve, you will see that particles greater than 250, but less than 500 are retained. Okay, and the number 5 will be all the particles which are below 250 millimeters. So if you go back and look into the methodology, you will see that many methods are by gravimetry. You do not know it is particle gravimetry. You think it is a sieving method, but it is a sieving method. But you weigh the particles in the different sieves. So this is a gravimetric method. Extraction gravimetry you have done but may not have realized it. Here it is when the analyte that you are looking at is not in a particular particle matter, but it is in homogeneous solution. The principle of extraction gravimetry is to use a solvent or any other material which can extract only the analyte of interest. Then after extracting it with a solvent, you evaporate the solvent and you can determine the analyte mass. And that mass gives you the mass of the analyte, which is extraction gravimetry. You have been doing it day in and day out, but do not realize. But the total fat estimation by Soxhlet extraction is a very good example of extraction gravimetry. Also, if you look at oleoresins in spices, that also is an example of extraction gravimetry. So you're extracting it into a soluble solvent and then removing the solvent and weighing the analyte. Particulate gravimetry has got several examples. It can also be used, as I've explained, to analyze or accurately uh, find out the suspended solvents in water sample. So you just filter the water sample, dry the filter paper, and the weight of the difference in the weight of the filter paper before and after gives you the uh, total I think, suspended solid. In microbiology, also we use particulate gravimetry, especially in the analysis of coliform bacteria, where an appropriate sample of water is passed through a particular filter, that is a 0.045 micron membrane filter. The filter is placed on a sterilized absorbent pad, saturated with the culturing media, incubated, and the coliform bacteria are identified by the presence of the individual bacterial colony. An example of extraction, particulate gravimetry extraction, is the crude fat content in chocolate, where you can extract it with ether for 16 hours, evaporate the ether, and get the fat content of it. So through this webinar, I have explained to you the process of volumetric analysis, the 4 different types of titrations, and gravimetry, the importance of gravimetry, and the importance of all the equipment that is required for volumetry and gravimetry. So I will meet you once again when I take the webinar on centrifugation on 10th June at 4 p.m.